Here's what most people don't realize about a Lego brick. It isn't just a toy, it's an aerospace-grade engineering component, manufactured to a tolerance of 0.02 of a millimeter. To put that in perspective, a human hair is roughly 70 thousandths of a millimeter wide. The dimensional precision of a Lego brick is 35 times finer than that. Why does precision matter for a children's toy? Because everything depends on a single engineering property called clutch force, the resistance you feel when two bricks connect and when you pull them apart. Too loose, and structures collapse under their own weight. Too tight, and a child can't disassemble them without help. The acceptable window is incredibly narrow, and Lego must hit it every single time, across every single brick, at a production rate of roughly 400 million bricks a day. So how do they do it? It starts long before the factory floor, with the material itself. Every Lego brick begins as ABS plastic, acrylonitrile butadiene styrene, delivered to the production facility as small, colorless granules, each barely the size of a grain of rice. ABS isn't chosen at random. It's the result of decades of materials testing. The polymer has a specific combination of properties that makes it almost uniquely suited to this application. It's rigid enough to hold precise dimensions under load. It's just slightly flexible enough to absorb the snap of two bricks connecting without cracking or deforming. It bonds to pigment reliably and evenly, and it holds its shape year after year without warping, yellowing, or degrading the way cheaper plastics do. Before any production run begins, the raw granules are combined with a pigment concentrate in exact proportions. Lego maintains a color palette of more than 60 standardized shades, each matched to a precise color code. A red brick produced in Denmark must look visually identical to a red brick produced in Hungary or Mexico. Color consistency isn't cosmetic, it's a manufacturing standard enforced as tightly as dimensional precision. Once the material is blended, it feeds into the heart of the factory, the injection molding machine. Melting. The blended granules pour into a hopper at the top of the injection molding machine. Inside, a long rotating screw, heated to approximately 232 degrees Celsius, pushes the granules forward while simultaneously melting them into a thick, viscous liquid. Think of it like a heated auger, continuously feeding molten plastic toward the front of the barrel. The machine itself is roughly the size of a transit van and weighs several tons. It runs continuously around the clock. As the screw turns, the molten plastic accumulates at the tip, building up a precise measured charge, ready for the next injection cycle. Timing here is critical. Too little material and the mold cavity won't fill completely. Too much and excess plastic flashes around the edges of the brick, creating imperfections that would disqualify it from the production line. Step 2. Injection and molding. When enough molten plastic has gathered, the injection stage begins. The screw drives forward like a piston, forcing the liquid plastic through a narrow gate and into a precision steel mold at extraordinary speed. The entire injection happens in a fraction of a second. The mold itself is clamped shut under up to 150 tons of force. That clamping pressure is what keeps the two halves of the mold sealed as molten plastic rushes in at high pressure. Without it, the liquid would force the mold open, escaping as flash. Thin, unwanted fins of plastic around the edges of the brick. Inside that mold is a cavity machined to almost incomprehensible precision. Every stud, every wall thickness, every internal tube is etched into hardened steel to within 0.02 of a millimeter. Lego designs and machines their own molds in-house at their facility in Billund, Denmark. A single mold, one which may contain cavities for 8, 16, or even 32 bricks simultaneously, can cost several $100,000 to produce. And because the mold is the precision, there's no tolerance for error. Either the mold is right or it goes back to be remachined. Cooling. The moment the mold fills, cooling begins. A network of channels built directly into the steel mold body floods with cold water, rapidly dropping the temperature of the freshly injected plastic. This cooling phase takes approximately 7 to 10 seconds, fast enough to lock the brick into its exact shape before the plastic has any chance to warp, shrink unevenly, or pull away from the mold walls. When the cycle is complete, the mold opens. A set of ejector pins, built into the mold, push the newly formed brick free from the cavity in a single clean motion. The brick lands on a conveyor belt, warm to the touch, finished. From molten liquid to solid, dimensionally precise brick, approximately 15 seconds, start to finish. Inspection and quality control. The bricks don't travel far before the first check. High-speed optical sensors scan each brick as it passes along the conveyor, checking surface finish, color consistency, and dimensional accuracy. Any brick that falls outside the accepted tolerance band, even slightly, is automatically diverted before it can advance further in the process. Rejected bricks don't go to waste. A BS plastic can be reground and reintroduced into the production cycle at controlled ratios, blended with fresh granules. For specialized pieces, minifigure faces, printed tiles, road signs, and other decorated elements, an additional step applies: pad printing. Unlike sticker-based decoration that can peel, bubble, or misalign over time, LEGO applies printed detail directly to the plastic surface using a process called pad printing. A small silicone pad picks up ink from a precisely etched metal plate and transfers it onto the brick surface in a single press, with registration accuracy measured in fractions of a millimeter. Multiple colors can be applied in successive passes, each one landing in exact position relative to the last. The result is decoration that bonds chemically to the ABS surface and won't lift, fade, or crack under normal use. Here is the detail that stops most people when they hear it for the first time. A LEGO brick manufactured in 1958, the year the current stud and tube design was patented by co-founder Gottfried Kirk Christensen, will still connect with a perfect, satisfying click to a brick made this morning on a production line in Billund, Hungary, or Mexico. Not approximately, perfectly. The dimensions haven't changed, not by accident, by absolute deliberate engineering commitment. Every time LEGO considers modifying the geometry of a brick to improve clutch force, to add a new surface feature, to refine a mold, the new design must be tested against archived bricks from the company's historical production. If a new mold fails to engage cleanly with a brick from 1963, the mold goes back. Compatibility is non-negotiable. In an era where consumer products are redesigned every 2 or 3 years, where software updates break older hardware, where replacement parts become unavailable, where backwards compatibility is an afterthought, LEGO has maintained the same core dimensional standard across more than 65 years of continuous production. No other consumer product on Earth makes that claim and keeps it. From the conveyor, finished bricks travel through pneumatic tube systems into large collection bins, sorted automatically by element type, color, and size. From those bins, they feed into the assembly and packaging lines, where the correct quantity of each element is counted, verified, and combined with instruction booklets before being sealed into boxes. LEGO's internal parts counting accuracy is within less than 1% of the listed bag count. Miss a single piece in a 500-part set, and the customer experience fails, which is why the counting systems downstream of molding are nearly as precise as the molding process itself. From a small pile of colorless granules, each smaller than your fingernail, to a brick that a child in Tokyo, a designer in Copenhagen, and an engineer in Sao Paulo can all trust to behave in exactly the same way. It is, in every technical sense, one of the most precisely manufactured consumer objects in the history of mass production, hidden in plain sight in every toy box in the world.